In part 3 of Module 4, we're going to continue our discussion of the first law for open systems by looking at turbines and compressors. So if you don't know this already, a turbine is actually a rotary machine whose purpose is to produce shaft work. And there's many different types of turbines that we know about. For example, steam turbines have steam leaving the turbine that passes through a condenser where it is condensed to a liquid, for example, or you have gas turbines where we have gas go through a turbine, create some electricity, and then the gas goes to the atmosphere. So turbines are usually used in thermodynamics to drive an electric generator and to drive the electric generator in power plants. So we usually associate turbine work with power plants, but turbines can also be used in, for example, cars where we have turbochargers where we use a turbine to create more power for the engine. So the idea of these turbines is to create shaft work. Now, on the contrary, a compressor is a device that is used to increase the pressure of gas by putting in some shaft work. So essentially, a compressor is the opposite of a turbine. It rotates, it allows us to increase the pressure of a gas by inputting some work to rotate a shaft, whereas a turbine is using the gas motion and the gas velocity in order to rotate a shaft. So we usually draw a symbol for a turbine. We draw it like this. We usually draw it something like this. And we're going to be looking at turbines and compressors a lot more throughout the semester, especially in the following modules. But a turbine would look something like this. So we have a turbine with a shaft, and we have some sort of inlet here. And this inlet is an inlet of gas coming in or liquid coming in. And we usually have an outlet at the bottom or an exit at the bottom. So we have an inlet and an exit, and this gas going through this turbine actually starts rotating this shaft, and we get some power out of the shaft or some work per second, essentially. And usually for a turbine, we can say that the velocity exiting is greater than the velocity coming in. And we can also say that the pressure exiting is less than the pressure coming in. So we're actually using the turbine to increase the velocity of the fluid, and it passes through the system so that we can increase the work. Okay, now the process of a turbine works in the following ways. So we have fluid passing through a series of nozzles that expands it to a lower pressure and a higher velocity. So we use a bunch of nozzles to increase the velocity, and this high velocity of the fluid is then directed onto moving blades in which the velocity is finally reduced by applying the torque to the rotating shaft. Okay, so you can read more about how turbines work in your textbook as well, but that's generally the summary. Now, on the contrary, a compressor, and we usually draw compressors in just the opposite direction, but it's pretty much the same thing. So our compressors look something like this. We have an inlet once again, and an exit in the same way. But now, the goal of our compressor, so this is a compressor, or we can write it as comp. The role of our compressor is that it uses work. So work is coming into the system, or power is coming into the system to increase the pressure of the system. So the pressure at the exit is greater than the pressure at the inlet, and we can say that the velocity at the exit is less than the velocity at the inlet. Okay, so it's a way for us to increase the pressure. And there are different types of compressors. This is a rotating compressor, so we're going to be looking in this class at rotating compressors mostly, but there are other ways to compress gases as well. For example, looking at screw compressors or other types of compressors. Okay, and the first law analysis for this system essentially looks at control volume that is determined by the green lines that I'm drawing right now. And we see that we have one inlet, one exit, and now we also have some power out of the system for our turbine. And for our compressor, we have some power into the system. Okay, and we're going to do an example of a turbine now to sort of try and understand what's happening and how this system works and solve a problem using the first law. So I'm going to copy over a diagram and a question so that we can solve it in this next part. So the question says that steam flows through an adiabatic turbine. Okay, so we know that we have a turbine. So we know that we have a turbine in our system, and this turbine is an adiabatic turbine. So we can highlight this word, and we're going to define what this word actually means. It tells us that the inlet conditions of the steam are 4 megapascals, 500 degrees Celsius, and 80 meters per second, and the exit conditions are 30 kilopascals and 92% quality and 50 meters per second. It says that the mass flow rate of the steam is 12 kilograms per second. Determine A, the change in kinetic energy, B, the power output, and C, the turbine inlet area. So we have three terms to determine. And really, the first thing that we can write out here is some of the assumptions that we're going to make. So whenever we have a turbine and we have no leak in the turbine and the mass flow rate is a constant 12 kilograms per second, we can say that we have steady flow. So some of the assumptions we can make is that we have steady flow, and we can also say that the change in potential energy is equal to 0. We're not told anything about the height or anything like that, so we're going to assume that the potential energy is equal to 0. The change in potential energy is equal to 0. The change in kinetic energy is not equal to 0. We have two different velocities at the inlet and the exit, therefore we know that kinetic energy has something to do with this. And actually, part A of the problem tells us to find the change in kinetic energy. Okay, it actually tells us what is the change in kinetic energy. So the first thing we can do in this system is the following. We can figure out what our state at the entrance and our state at the exit of the system are. So in this problem, you can see that the book defined the terms at the entrance with 1, 2, and 3, 1, and the terms at the exit with 2. So I like to always keep it as I and E. The book uses 1 and 2. So there's a specific reason why I like to keep it as inlet and exit and not 1, 2, 3, 4, 5. And we'll talk about that reason a little bit later when we look at transient systems. But essentially, whatever you prefer using is fine as a denomination. I'm going to follow the book's way of doing it for this problem because it gives it in the problem like that. But we can write that at state 1, which is our inlet, so little I, and we can write a state 2, which is our exit. So up to you whether you want to use 1 or I. I prefer using I and E, but the book prefers using 1 and 2, so we'll go with 1 and 2 this time. So we have that given that P1 is equal to 4 megapascals. We're also given that T1 is equal to 500 degrees Celsius, And we're given that velocity 1 is equal to 80 meters per second. And then at state 2, we're told that pressure 2 is much lower. It's equal to 30 kilopascals. And x2 is equal to 0.92, so we know it's a saturated mix. And V2 is equal to 50 meters per second. Okay, and using this information, our first part of the problem is finding the change in kinetic energy. And the book doesn't specify this, but I would specify this in a problem that I would give you. They should give you the units for the change in kinetic energy they're looking for. So the change in kinetic energy they're looking for is divided by mass. So it's in kilojoules per kilogram. Okay, and that makes it very important because we don't have to know the mass inside the system. We just need to find the change in kinetic energy with respect to mass. So instead of having to find delta KE, we're actually going to be finding delta KE over mass, which is equal to a specific kinetic energy change. And that's what the book is looking for, but doesn't really tell you in the problem, which I think is not great, but it is the way it is. So we're looking for this term right here. And from this term, we know that in our first law, the change in kinetic energy is usually equal to, if we only look at the kinetic energy terms in our first law, we know that the change in kinetic energy is equal to 1/2 V2 squared minus 1/2 V1 squared. Okay, those two are our terms for kinetic energy. So what we can do is we can find our change in kinetic energy because we already have velocity 2 and velocity 1. So we're just going to write 1/2 times 50 squared minus 1/2 times 80 squared. And we're going to find that our change in kinetic energy in the system is equal to minus 1950 meters squared per second squared. Okay, and now with this rule of meters squared per second squared, we can convert this and say that this is 1950 joules per kilogram. And we know in this class we usually like to have kilojoules per kilogram as our system default and our unit default, because joules are very, very small, so we prefer using kilojoules per kilogram. So we can divide this term by 1000, just like you would do in your actual equation for the first law, and you would get that this is equal to minus 1.95 kilojoules per kilogram. So this is our change in kinetic energy specific, okay, divided by the mass. So per mass, we know that we lose 1.95 kilojoules of energy throughout our system. And it makes sense, right? Our velocity is higher at the entrance and the exit, which means that throughout the system, because we're powering the turbine, we're losing speed as we go through the system. Okay, so moving on from that, we can go to part B. So part B says we should look for the power output. So power output is W dot out. Okay, that's our power output. And W dot out is equal to power. And we can remember that W out, not W dot out, but just W out would be the work. Okay, so that's the difference between W and W dot. So whenever they ask for the power, they're looking for W dot. So to find the power output, we know we have to use the first law. By using the first law, we're able to find the power output, and we're going to use the first law for steady flow and analyze our turbine with it. So our first law for steady flow says that Q dot in minus work dot out is equal to M dot out, or M dot E. Let's leave it as M dot E so that we don't get confused, times HE plus VE squared over 2 plus GZE minus M dot I times HI plus VI squared over 2 plus GZI, and that's our equation. And we have one inlet and one exit in our diagram. If we look at our diagram, we have only one inlet here and only one exit here, and we have this work coming out of our system. So we only have one inlet, one exit, so it makes it very easy for us to solve the problem. The equation stays the same, and now we can cancel some terms out. So the first term we can cancel is this one. We can cancel the z terms because we're not given any information on z, and we can simplify our equation to have everything in terms of 2 and 1s, because we called state E 2 and state I 1. So we can rewrite our equation as Q dot in minus work dot out is equal to M dot 2 times H2 plus V2 squared over 2 minus M dot 1 times H1 plus V1 squared over 2. Okay, that's our most general equation. Now, some further simplifications we can do. We know that we have steady flow, therefore we know that M dot 1 is equal to M dot 2. The mass coming in is equal to the mass coming out. So the mass terms can just be called M dot. Okay, that was given in the question already, but we can assume that. The other assumption we can make from the question, and not really an assumption, but information given from the question, is that in the question we're told that the steam flows steadily through an adiabatic turbine. Adiabatic means that Q dot is equal to 0. It means there is no heat transfer. It's fully isolated, essentially. There's no heat transfer from in or out of the system. So essentially, if you would have some heat loss, you would have a Q dot coming out. In this case, there is no Q dot coming out. So Q dot is equal to 0. That's what adiabatic means. So if Q dot is equal to 0, that means that we can get rid of our Q dot in term. So our Q dot in term goes to 0. And so we're left with the equation that says minus work out and minus work dot out, which is power, is equal to M dot multiplied by H2 minus H1 plus V2 squared minus V1 squared over 2. And here, if we were to compute our kinetic energy from this point, we would compute it and divide by 1000. So we would add our 1000 term here. Now, we've already computed this term. This is part A, so we can just plug in for this term from part A. So we have that, I'm just going to flip the signs just so we can find positive work dot out. So we have work dot out is equal to negative mass flow rate times H2 minus H1 minus 1.95 kilojoules per kilogram, because we already computed it in part A, so I'm already going to plug it in. And the mass flow rate, we can actually substitute our value for mass flow rate, which we already know, which is minus 12. So we have all those terms, and we're left with finding this term and this term. So we have to find H1 and H2. So how do we find H1 and H2 for steam? Well, we're going to go to our tables because we have steam. So if we have steam, which is water, we're going to go to our tables. So for H1, we know that we have, at state 1, we have P1 is equal to 4 megapascals. And at temperature 1, we have 500 degrees Celsius. So from this, in the tables, we can find that H1 is equal to a certain value. So we're going to go to our tables, and we're going to figure it out. So we have pressure 1 is equal to 4 megapascals. So we're going to go to our saturated mix table, table A5 first. So we're going to go to table A5, and we're going to go to 4 megapascals. So table A5, which means it's at 4,000. We have a value of 4,000 here, which is 4,000 kilopascals or 4 megapascals. And we see that our temperature of saturation is 250 degrees, 250.35. So our temperature is 500 degrees. That means we have a superheated vapor in our system. So we're going to go to the superheated table. We're going to go to 4 megapascals, which is shown on this page right here on the top left. So we have 4 megapascals, and we're going to match 4 megapascals with 500 degrees. And so we find that our H value is 3,446 kilojoules per kilogram. So we can write that H1 is equal to 3,446 kilojoules per kilogram. Now, in order to find H2, we can use our information at 2. So we have P2 is equal to 30 kilopascals, much lower pressure, and we're told that X2 is equal to 0.92. So we know that we have a saturated mix. So we're going to go to our pressure table, and we're going to find HF and HG because we know it's between HF and HG because we have a saturated mix. So if we go to that table, we go to table A5 at 30 kilopascals, and we have an HF, which is equal to 289.27, and an HG, which is equal to 2,624.6. So I'm going to write those down. HF is equal to 289.27. HG is equal to 2624.6. And now, for 2, we can find H2 by the quality. So we can say that H2 is equal to HF times 1 minus X plus Hg times X. And by plugging in the values, we get that our H2 is equal to 2,437.7 kilojoules per kilogram. And now we have all our terms for our above equation. So we can plug in our terms into our above equation, and we get that work dot out, or power out, is equal to 12,123 kilowatts, which can also be written as, if we want to, 12.1 megawatts. Okay, whichever way we want to write it is fine. Okay, now part C of the problem, because we're using velocity, asks us to find the turbine inlet area. So let's go to part C just to show you. So part C says the turbine inlet area. So we're supposed to find the area of the inlet, which in our case is at point 1. So we're looking for area 1. Okay, and we know a few of our equations. We know that we have mass flow rate is equal to density times area times velocity. And so we can write this for point 1, so density 1, A1, and V1. And this is also equal to A1, velocity 1, over specific volume 1. So if we can find specific volume 1, we already have velocity, we already have the mass flow rate, we can find the area. So area 1 is equal to mass flow rate times V1 over velocity 1. And the value for our specific volume is actually from our tables, and I'll let you do this in your own time, is equal to 0.08644. So plugging in the values for velocity and mass flow rate, we get that area 1 is equal to 0.0130 meters squared. Okay, and that concludes our problem using a turbine as an example. So now we're going to move on to another type of system that we can analyze using our analysis for open systems, and that is looking at a system called a heat exchanger. And what a heat exchanger is, it's just a device where two fluids or two moving fluids exchange heat without mixing. And this next example that we're going to be doing is actually going to be an example of a heat exchanger. Okay, so we're going to do an example of this, but essentially what we have is we usually have a fluid that is cold and a fluid that is hot, and they are flowing in side by side, and there's some heat transfer between the hot fluid and the cold fluid, which changes their temperature as we go. So a pretty simple system. You've probably already heard of heat exchangers, but it is what we use in our refrigerator systems, for example. And R134A is used a lot in these types of heat exchanger system. So let's copy over the example and then see how we can draw a diagram of what is happening. So bear with me while I copy over the example. So we have an example that says cold water leading to a shower enters a thin-walled double pipe counterflow heat exchanger at 15 degrees Celsius at a rate of 0.6 kilograms per second, and is heated to 45 degrees Celsius by hot water that enters at 100 degrees at a rate of 3 kilograms per second. Determine the rate of heat transfer in the heat exchanger and the exit temperature of the hot water. So we have a problem, and this problem shows us that we have a double pipe counterflow heat exchanger. So what a double pipe counterflow heat exchanger is just a heat exchanger with two different pipes that are flowing against each other. So we're going to draw the hot water pipe going in this direction, and we have some hot water that's going in this direction. Okay, so this is going to be the hot water. And we're told that this hot water enters at 100 degrees. So we know that the temperature of the water is 100 degrees and comes in at a rate of 3 kilograms per second. Okay, so we have a rate of 3 kilograms per second and 100 degrees. Now, on the other side of the double pipe counterflow heat exchanger, we have another pipe that we can show that is sort of around it. So if we look at a side view, our hot water would be flowing through here, and then cold water would be flowing all around it. Okay, this is our cold water. So we're going to draw our cold water walls in blue. So we have something that looks like this, where we have some cold water coming in through here and exiting through the other side. And so essentially on our front view, it would look like this. We would have a pipe coming in with some cold water and exiting on the other side somewhere with some warmer water, and then the hot water would just come in through the middle, right here, through the middle of that pipe. You would just have water coming in if you're looking at a front view of that system. Okay, so we're told that the cold water, and I'll write in white just so it's clear, but we're told that the cold water is at 15 degrees Celsius, and we're told that the flow of the cold water is 0.6 kilograms per second. And we're also told that the water is heated to 45 degrees by the hot water. So we know that the exit temperature is 45 degrees Celsius. Okay, so that's the information that we're given. Okay, now we're told in the question that we have to determine the rate of heat transfer in the heat exchanger. Okay, so the rate of heat exchange in the heat transfer, the rate of heat transfer in the heat exchanger is the following. We agree that we have more heat on this side than on the cold water side. So what's going to happen is we're going to have some heat going from the hot side to the cold side of our system. So we're going to have some amount of heat from the hot side to the cold side. We're just assuming this, but we're pretty sure that that's what's going to happen. Okay, we're not 100% sure, but it makes sense that if we have hot water mixing with cold water, the heat is going to be leaving the hot water and going to the cold water. So this is what we're looking for, determining the rate of heat transfer. And we're also going to be looking for the temperature at the exit of the cold water. So we're looking at temperature of exit of the hot water as well. Okay. Now, one thing we can say about heat exchangers is that because there are no moving parts, we can say that the power is equal to 0, or the work dot is equal to 0. We can also, in some cases, and in this case, we're not given any details on the velocity of our fluid. If we're not given any details on the velocity of our fluid, we can assume that delta KE and delta P is equal to 0. If we were given velocity at the inlet or at the exit, not just mass flow rate, then we would have to take into account our kinetic energy change. Okay? Now, how do we go about solving this problem? We now have two systems within one. So we're looking at an isolated system. So the first thing we can say is that, as an assumption, because we're not given any information in the question, is that we have steady flow. Okay, so that means that the mass flow rate stays constant throughout for both systems. And we have two systems. Okay, so the other thing we can say is we have two systems. Okay, we have a cold water system and a hot water system. So we can treat them separately or together. We can decide what we want to do. The other thing is we can also say that the heat transfer to surroundings is 0. So we're going to assume that the system is well insulated. So we're not given any information on any heat transfer to the outside of the whole system. So the outside would be anywhere outside of this boundary right here. We're not given any information on the outside of this boundary where we would have, for example, we could have some Q dot coming out, but we're not told any information on that. So we're just going to ignore that for now. We're not going to be using that for now. Okay, we're going to be saying that that's assumed to be equal to 0 because our system is well insulated. Now, the other thing we can write is that we are not given pressure. We're not given pressure or specific volume. And since we're not given pressure or specific volume, it is going to be hard to use tables. So this is one of these special cases where we're going to actually be using CP for water. So we're going to be using our definition that H2 minus H1 is equal to CP T2 minus T1 as opposed to using the tables. The reason we are going to use that is, first of all, because it tells you in the problem what CP is. So that's the first hint. The second hint is that we only have one property of the water at the entrance and one property of the water at the exit. So we don't have two properties in order to find more of them. So we're just going to have to assume that we're going to use CP for this problem. Okay, a little bit of a special case. Okay, and I wanted to show you that because of that. So moving on from that, we now have to apply the first law to our system in order to find our Q dot. So how do we go about this? Well, there's two ways we can do it. We can apply the first law to the cold water side, or we can apply the first law to the hot water side. And reminder, our goal is to find Q dot. So our goal is to find Q dot. The other thing we could do is do the first law for both. So if we do the first law for both and we look at both systems together, Q dot is equal to 0, right? Q dot for both is equal to 0. Because in the first law for both, we said that our system is isolated, therefore Q dot going out of the system is 0. However, if we look at only one side, so let's do the hot side with a boundary in red. So we just look at the boundary for the hot side. We see that there is some heat going out into the cold water side. Now we can do the boundary of the cold side in green. Okay, so just looking at the green side, just looking at the cold side, we can see that crossing this boundary, we have some Q in now into the green side. So which side are we going to use in order to find Q? Well, we can choose either side, but a rule of thumb is if you have more information on one side than the other, which we do on the cold side, then we want to start by doing the first law on the cold side first. So we want to use the first law on the side that has the most information. Because if we started on the hot water side, we're not going to have enough information in order to find our Q dot, essentially. So what we're going to do is we're going to choose to do our cold water side first. And I'm going to write in green so that we know that it's the green side in our diagram. So the first law for our green side for the cold water is going to give us the following equation. We're going to have that Q dot in minus work dot out is equal to M dot HE of the cold water. I'll put CW for cold water minus M dot HI of the cold water. And we got rid of our kinetic energy and our potential energy terms because they're equal to 0. We also know that work out is equal to 0 because we're told that in a heat exchanger we have no moving parts, therefore we just have that solution. And going further than this, we also can redraw our diagram just with the green, but if we look at the green, it makes sense that we have Q into our system, right? Our Q is coming from the red to the green, so it's coming into our system, so this should be positive. This green term should be positive, okay? Because this Q in term should be positive because we know that there's some energy coming into the cold water, okay? There's some heat coming into the cold water. So going ahead and solving it, we can say that Q dot in is equal to M dot times HE minus HI, and that's for the cold water. And we know that HE minus HI, we can actually write TE minus TI times CP because we're going to assume that we can use CP for this type of problem because we don't have enough information to find HE and HI. So we can write M dot we're going to use the definition of HE minus HI, which is CP times HE minus, CP times TE minus TI. And from there, we can plug in the values. We have all the values for these, so we can say that M dot is equal to 0.6, multiplied by CP is 4.18, given in the problem statement, multiplied by 45 minus 15. And we can keep it in Celsius here because we have a difference in temperature. Okay, if we didn't have a difference in temperature, we wouldn't be able to use Celsius, but in this case, we can. So you get that this is equal to 75.24 kilowatts. So Q dot in is positive, which makes sense because we added some heat to the system, which means the temperature went up. Okay, it makes sense from a logical standpoint. Now, let's look at so we've solved the first part of the problem. The second part of the problem asks for the temperature at the exit of the hot water. So I'll put TE of the hot water, THW. So now we're asked to find the temperature at the exit of the hot water. So what we can do is we can now do first law looking only at the hot water. And this first law for the hot water, I'm going to keep in a white color, okay? So just remember when you're reviewing this problem that it's going to be in white. And we can say that in the same way as the other system, Q dot in of the hot water is equal to M dot of the hot water multiplied by CP of the hot water times TE minus TI of the hot water. And we can plug in our values to try and find TE. So we're looking for TE. So we can rearrange the equation to find TE, but let's plug in our values to this equation. So this is our equation. We simplified it already because it's very similar to the first first law for the cold water. So it's pretty much the same equation that we have to work with. Now we know this term. We know this term, and we know TI. Do we know Q dot in? Well, let's look at our diagram really quick, and let's just zoom in to our hot water alone. And I'm going to redraw it just for the hot water. So if we look at the hot water system, we had put a boundary in red. And this boundary in red, we had said that Q dot was leaving to the cold water. Okay, so this is Q dot. Now Q dot is leaving the hot water system, okay? And we also know that this Q dot is equivalent, so this Q dot out, let's say, is equal, so this Q dot out is equal to the Q dot in for the cold water. Okay, it's equal. If the cold water is taking in heat from the hot water, then we can say that Q dot out is equal to the Q dot in of the cold water. And so that means that Q dot out for our hot water is equal to 75.24 kilowatts. So we know that there's 75.24 kilowatts coming out. Now, going back to our equation, what is Q dot in? Well, Q dot in is just the opposite of Q dot out. So that means that we can say that Q dot in for a hot water, there is no heat in, so it's just going to be the negative of Q dot out for our hot water. Okay, so our Q dot in is actually going to be negative 75.24, which means that the heat is actually coming out. It makes sense. Okay, so if we had assumed that Q was coming into our system, we would say that it was just a negative because it's actually coming out of our system. Okay, so make sure that you really understand this. So we can go ahead and write that our equation is equal to minus 75.24 is equal to 3 multiplied by 4.19, okay, which is our CP given for our hot water, multiplied by T2 minus 100 degrees Celsius. And again, we don't have to convert to Kelvin, but you can if you want to, because we're looking at a difference in temperature. And we find that temperature 2 is equal to 94 degrees Celsius. So we can see that the hot water has cooled down by exchanging with the cold water to 94 degrees Celsius. And in the process, actually has increased the cold water temperature from 15 to 45 degrees. And that concludes our second example problem that covers heat exchangers and how they work. So in part 4 of module 4, we're going to be looking at the transient process and deriving the equation for the transient process, and then looking at an example problem for this one. So we'll see you in part 4.